There we go. Hi, everyone. Thanks for coming. It's so exciting to see so many people here for my talk, which is really actually about computer history. This is not just a stock image of some RAM. This is actually a 16 megabyte RAM module from a 1980s supercomputer. This is the Encore Multimax. And the reason that the Encore Multimax is up here is because this talk is about the virtual memory subsystem that was written to run on this. So in like the mid-1980s, 1986, 1987, if you had $250,000, this is what you were buying. I don't know if there are many Encore Multimax hackers out there, but maybe some more of you are more here because you're interested in the Sequent Balance 21000. Maybe some digital equipment folk, the Microvax 2. Anyone want to pop a Microvax 2? That guy. Or the Sun 3 also had a port of Mach virtual memory. There's a few more of you are interested in the PlayStation 3, PlayStation 4, PS Vita. Also run code derived from the same virtual memory subsystem that I showed that was running on that Encore Multimax from 1987. And this company also uses it. And so the question I want to try and answer with this talk, and also with my sort of giving some insight into my approach to this topic, was to ask not what is it that this code does, but why was it designed in this way? And how can I get a deeper understanding in order to actually find the deeper, more interesting, more meaningful bugs? Like, I've been looking at the XNU code base for well over a decade now, and have opened vmmap.c many, many, many times. This is noises from the pipes. Opened vmmap.c many, many times, and it is an extremely overwhelming, intimidating code base with functions, C functions that are multiple thousands of lines long that 1,500 lines in decide to recurse. It's a really intimidating thing that it's always been easier to just find something else. And so the thing to focus on is not, well, what does each line do and how do I approach it this way? It's instead to ask, why is it designed in this fashion? What's the history of it? And what can I learn from that? And so in order to answer this why question, we need to go back. We need to go way, way back, 35 years to October 1987. Carnegie Mellon University publishes this paper, the documentation for iOS, for your iPhone 14 Pro Max. Machine-independent virtual memory management for page uniprocessor and multiprocessor architectures. And this entire talk and all my research is really based on everything that's in this paper. And I don't want to go too deep into Silicon Valley trivia, but some of those names might be familiar to some of you. This first person is the founder of Microsoft Research, which he led for 20 years. The second guy is also Silicon Valley celebrity, former SVP of software at Apple before Craig Federighi. It's a pretty impressive group of people that put this stuff together. And at the time, Avadis was already working at Next and would later move to Apple to port that code base and this code base to become macOS. And the real insight is that in 1987, that code base was clean, minimal, elegant, and documented. And you can still get the code for that stuff from FTP servers. And that code, over the 35 years, well, that stuff is still there, plus 35 years of optimizations, new features, and churn that just make it impenetrable now. So we're going to go through first some of the necessary abstraction layers that they use so that we can figure out how these things are put together. And so the primary first object we're going to look at is the VM object. This is a very abstract object that you can think about as just representing some contiguous set of bytes. It's a very abstract idea that you never directly interact with. And these VM objects hold something more concrete, which are VM pages. These are resident pages that every page pointed to by a VM object indicates that that page is somewhere in physical memory. I'm going to use the convention here that these VM object structures seem to grow and shrink, but in reality that's not the case. A VM object is actually just a small structure, and the size is just a field. And the actual amount of memory that these VM objects are using grows and shrinks based on the length of the linked list of VM pages which they are managing. And I'm also going to use the convention that rather than showing the linked list, we're going to show each page attached to the VM object to say our VM object represents this large abstract collection of bytes. In some cases, we don't know what the values are there, and in some cases, we have a physical page which is containing the real values there. So these orange pages are actual things which are in memory. So one of the key aspects of Mach, at least in 1987, is that they had a very well-defined and strong separation between two different layers. They had an upper layer of very abstract code that we'll call the VM map layer, and then a separate lower level layer called the PMAP layer, where the PMAP is the machine-dependent layer that actually represents, for all of the different, you saw already, the wide variety of devices that this code ran on, that was all isolated in the PMAP layer, and then the VM map layer performs all higher level operations. The VM map layer is more abstract, PMAP layer is concrete, machine-independent, and independent. In fact, if you go and read that paper from 1987, they say that they got a student who didn't know C to port the VM map PMAP layer to a new architecture in 2 weeks, which I wouldn't necessarily recommend as a great development practice. But nevertheless, it shows that at that time, it was a relatively contained and small set of code. These VM objects themselves, you cannot interact with directly. So from user space instead, the entry point that you have is a VM map. If anyone's even tangentially familiar with the iPhone exploit and jailbreaking scene over the last 10 or 15 years, you'll have heard of task ports. Well, what the primary use of the task port is to give you a way to interact with a VM map. There is a one-to-one mapping between a task and a VM map. These VM maps then represent the entire virtual address space of a task. That's implemented as a linked list of VMEs, virtual memory entries, each of which represents some contiguous region of virtual address space within a task, linked together. And then each of these VMEs, in turn, points to a VM object. Then the last step of the puzzle would be that the VME can point into a particular offset in an object and then a particular size. And this can continue then for all the VMEs. And this is then the complete setup for the abstract version of what will fill your virtual address space. And then it gets a little bit more complicated. So one of the fundamental things to realize here is that VM maps and VMEs and VM objects themselves don't actually have inherent protection. There's no notion of a read-only VM object because no one interacts or should directly interact with a VM object. All of the protection information is contained on the interface to the VM object, which are the VMEs. So for example, if you have a VME with writable protection, it means you are able to write to this VM object down here. Down below all of this, you have the machine-dependent layer, the PMAP, which they go to great pains to point out is merely a cache for what the VM map is representing. So the VM map is the source of truth for what the virtual address space should look like, and the PMAP reflects that. The VM map always contains what should be the correct information about your virtual address space. And indeed, this is where a lot of the interesting vulnerabilities lie. It's where the PMAP and the VM map layer get confused about what the state of reality should in fact be. So when we look at shared memory, we can have, for example, two separate tasks. We have the task on the left and the task on the right. And say we want to share the memory represented by the VM object on the left with the task on the right. The easiest way to do that is simply to create another VME on the right with another pointer into the VM object. If they both have read and write permission, then what we've created here is true shared memory. That is, both sides here can access all the physical pages represented by that VM object, and they can both read and write them as they want. And whilst there are plenty of interesting vulnerabilities that occur here, most of those are not occurring in the virtual memory layer itself. These are occurring at a higher layer. For example, time of check, time of use issues in device drivers or between user space and the kernel that happen to use shared memory. But there's another, perhaps more important form of shared memory where the semantics are implemented in the virtual memory subsystem. And this is when you are creating copy-on-write versions of memory. For example, on the PlayStation 4, when you're forking and execing, you don't want the child process to be able to manipulate the memory of the parent, but you also don't want to have to copy every single physical page that's resident in the parent's address space into the child's address space. So instead, what you can do is almost exactly the same as they did before, except you set one extra bit on the right-hand side here. You also set a bit on the left-hand side saying that we need to copy at some point later. And there's one extra thing which is very important. You also have to interact with the PMAP layer. Currently, those two pages, the task on the left has the ability to write to those pages, but we need to remove that writable permission so that if at any point in the future the task on the left tries to write to those pages, we, as the more abstract VM map layer, will get called by the fault handler, and we can resolve what's going to happen. And we'll look at what's going to happen now. So first we'll look at what happens when the task on the right wants to simply read through that copy-on-write copy of the VM object. Well, in that case, there's not actually that much that needs to happen. The task on the right, since it doesn't have any entries in its page table prior to this, when it tries to read that virtual address space, when it tries to read from that VME, a fault will occur, and the VM map code will come up, find the task's VM map, traverse the list of virtual memory entries to find the VME which covers this virtual address space. It will then see, well, I just need to follow, this is a fault for a read, so I don't need to perform any copying. I simply follow the pointer down to the VM object, find the resident page, and I can simply insert a page table entry into the PMAP, the page table, for the other task. It gets a little bit more complicated if that task on the right wants to write into that virtual memory object, because at this point we've not actually performed any copying operations. But it's not, but you can't write into that object on the left-hand side. So what instead happens is the VM map layer traverses down, finds the page, makes a physical copy into a new object, into a new VM page, which then gets wrapped in a new VM object. And the important part here is that it's only this page that was modified that needs to get copied from this VM object over here into here. All the other pages that we can freely read on this side do not need to be copied. Instead, we can say that this upper object now shadows the lower object over here. So any read access can simply follow the shadow pointer chain down to here and continue to simply manipulate page tables, whereas any write access will, again, need to perform this same copy. In this case, we then get a new page table entry representing this newly allocated page, which contained a copy of the contents of this VM page over here. And so you can see that we can start to create actually arbitrarily complicated chains of objects which shadow other objects, which shadow other objects. In some cases, we might modify the pages and create copies. In fact, we might sometimes have VM objects where we've caused a write fault on every single page, and we have now completely covered the underlying shadow object. And actually, this is not just a chain, these can be arbitrarily complicated tree structures of shadowing VM objects. And the original version of Mach, the paper, points this out and says, in most cases of excessive object shadow chaining can be prevented by recognizing that new shadows often completely overlap the objects they are shadowing. And this is the bit which might be interesting to the audience. Mach automatically garbage collects shadow objects when it recognizes that an intermediate shadow is no longer needed. So we can see in this case here what this means. So on the left, we have a shadow chain of 3 objects, where the upper VM object already has resident pages which completely cover anything which the VM object 1 layer below could ever contribute. And since this is the only pointer into this VM object here, actually these pages it cannot be the case that these are actually referenced in any page tables. These pages are actually available to be reused. And so that's what this garbage collection algorithm is trying to do. It's trying to traverse the trees of VM objects to find these redundant pages that it can make available for reuse. And so we'll come to the first bug. The algorithm that is actually there in the 1980s version of this code is much simpler, it's much more naive, and it's much more correct. But over the decades, many decades, many optimizations have been added, some of which work, some of which worked at some point, and some of which, like this, did not survive a transition to 64-bit and remain correct. So we can look exactly at what's happening here. So object here points to this top object on the top left-hand side. And what it's trying to do is take VO size, which is the size in bytes represented by this abstract VM object. And it's trying to say, is that converted into a count of pages equal to the number of pages, right? So it also stores this, it doesn't have to traverse the linked list to count the number of resident pages, it also just stores this count as they're added and removed. So it's trying to do something very simple here. If those two numbers match, then it's the case that they can drop a reference on the VM object and free all these VM pages because they can't possibly be referenced from anywhere. Now, of course, when we actually look at these things a bit more closely, well, VO size is actually a 64-bit value, and A to P is just going to shift that value down by page shift, which on ARM64 device is 14 bits, which means that, well, 2 to the 32 plus 14. So if we had a VM object with 4 and a lot of zeros after it, this is going to go kind of wrong. And you can imagine that when they were, well, and I say that this code wasn't there in the 80s. I was going to say, well, they couldn't even imagine having whatever this is, 100 terabytes of RAM. Of course, the real question is there even an interface to create such a large virtual memory VM object? If you just try to call VM allocate, malloc, it will fail. It doesn't want to create such a large contiguous VME. It wants to split things up into much smaller ones that are easier to manage. However, there is this completely unused extra API that you can call called Mach Memory Object Memory Entry 64, which allows you to pass a completely arbitrary size. And you can create one of these extremely large objects. And so what that means in practice is we can create 2 of these extremely large objects, with the upper one shadowing the lower one, and they each have one resident page. And then if we make the sizes of these, well, that value that's going to overflow plus the size of one 16K page, then what will happen is when the garbage collection tries to determine, is that upper object completely full, as in, does it have resident pages which must cover its entire size? Well, it takes the size, it shifts it down by 14 to get this value, and then it truncates that to a 32-bit integer, and it says, oh, well, in order to fill this object that should require 4 billion physical resident pages, it actually only needs to have one resident page, and indeed it has one resident page on the far right-hand side. It also has a read-only PTE that it's read from the lower shadow object, which is in its page table. So what this then means is that the garbage collection code will look down at that lower VM object and say, oh, well, it cannot possibly be the case that any VM pages contained in this VM object can be in any page tables. So it's totally safe to just drop the reference on that VM object and return this page to the free list. And the most important thing to realize here is that page table entry never gets updated because the VM map code believes that it cannot be the case that there were any references in the page tables to that VM page. And it doesn't proactively go and let's do an extra check and remove everything. Just to be sure, for performance reasons, it simply moves on and leaves you with what is effectively a dangling PTE in your page table. And whilst this is kind of cool, you are limited as to what you can do with this primitive. Namely, you only have a read-only page table entry here, albeit a dangling one that it will enable you, if you were to reallocate this freed VM page with something else, for example, some kernel page or something from another task, you could very easily read it. You cannot write to it. And so we're going to look at one other case study of a slightly more complicated bug that gives you that write primitive. And perhaps slightly strangely, you get the write primitive from an API that's designed for reading. So that paper in 1987 spelled out what at the time was the entire virtual memory interface. You had 9 methods, 9 different operations. And for any of you who've looked at iPhone stuff, these all look pretty familiar. Like almost all of those APIs are unchanged on the iPhone. And if you're doing regular low-level iPhone development, you are using these APIs. Now it's about 30, if not a few more operations. And then there was one way to read memory called VM read. Now you have MachVM read, MachVM read list, and MachVM read overwrite. So the setup that we're going to show here is using 2 VM maps, but really this also applies if you use these APIs to read from one map into the same map, but it's a little easier to visualize with 2 different maps. So we have the same setup here where we have each VM map having a linked list of VMEs which represent the virtual address space represented by those VM maps. Those VMEs in turn each point to VM objects that have some set of resident pages which actually provide the contents of the VM objects. So the simplest case for MachVM read overwrite is when you are copying page-aligned chunks, page-aligned and page-sized chunks of memory from one area to another. In this case, we could copy these 2 entire VMEs on the left over to these 2 entire VMEs on the right. And you can probably imagine that in this case, there's all kinds of virtual memory tricks that you could play here. You could maybe just move the VMEs themselves, or you could update the pointers of those VMEs to point to the VM objects, or you could copy the pages over. There are already a lot of ways that you could implement this and a lot of things that could go wrong. But to make it even more interesting, we need to make it more complicated. So the first thing we're going to do is make the regions that we want to copy be unaligned. So that means we're going to start copying a bit into the start of the first VME, which means a bit into the start of one of the pages, which also means in the destination, we're going to have to start manipulating memory in sort of some way into an existing page, which means we can't just simply throw the page away and make a copy of a new one. We've got to actually start manipulating these pages at a lower level. And to make things extra complicated, let's also put a copy on write copy of something right at the end here, which means that we've introduced another security property, which is that the resident pages pointed to by the VM object in the far bottom right must never ever be modified. Otherwise we break copy on write, and we break then all of the security properties which rely on that. The most important, which include, for example, the ability to have copy on write versions of files that you are able to read, but you're not able to write. And the title of this talk is MacDirtyCow. And prior to finding this vulnerability, I had never actually dug really deeply into how the original Linux Dirty Cow worked. But for any of you who do know how it works, it is remarkably similar to what I'm going to explain here. So yeah, let's carry on. So the way that this copying works, it's divided up into two loops. The first loop, on the right-hand side, we have the destination virtual memory area. The first loop is taking a lock on the entire VM map on the right, and then it's traversing the linked list of VMEs that cover the contiguous destination region, and it's checking, are they all writable? Because those VMEs, remember, that's all that defines what the correct semantics for these VM objects are. So they must have writable VMEs, otherwise we must not manipulate them. And that's fine, so it goes through. In this case, both of our destination objects have the writable bit set, so this is fine. Now it's time to actually do the copy. So it first has to go find the VM object for the source for the first bit of the copy, the VM object for the second bit of the copy, find the correct offset within those into the two underlying pages, and then it's going to call this method called VM fault copy. And the thing which should trigger alarm bells for anyone who knows how Dirty Cow works is that, well, they also unlock the destination map before they perform this copy. So VM fault copy is actually an extremely low-level copying operation where it's going to dig into those two VM objects, the source object and the destination object, find the resident pages, and then take the physical addresses of those resident pages and convert that into offsets into the fizz map, which is this region of virtual memory that has a one-to-one mapping with physical memory. And the actual copying happens inside the fizz map there. So let's again walk through and see what's happening in this case. So this is going to go and copy from the left-hand side to the right-hand side, and then it's going to move on and try and do the next destination VM object, which is still covered by that first VM object on the left-hand side. Now this VME is slightly different from the first one in that it's a needs copy, which means that it is under absolutely no circumstances allowed to actually write to those pages. The VME, although the VME is writable, you must not write to those pages. You must first what they call resolve the copy on write, which is exactly what the VME object shadow operation does. So the logic here is saying, if that entry has needs copy set and is mapped writable, then first perform a shadow operation, which means you take the VME and you insert this new shadow object, and your copy destination is actually that object, which has a copy of the page from the original VM object below, and you're going to copy into there. And this is the intended functionality. This is how it's supposed to work. But something is actually not quite right with the semantics here and with the logic. And as I say, if you know how DirtyCow works, almost exactly the same thing goes wrong. In that, well, what happens if we just switch this object between the first and the second copy on the right-hand side, because we have this point in the middle where the map gets unlocked, and we're free to modify it, even though there are some checks, even when the lock is retaken. But are those checks correct? So what if we instead do this? During this first loop where we walk through the VMEs holding the lock, we just put a regular anonymous internal memory object here. We have the writable bit set, so this is going to be fine. We perform the first copy, which copies from that first VM object on the left to the first one in the destination map. And while that's happening, the destination map is unlocked. So we are kind of free to just put a different VME here. We can put a needs copy VME, but we can also, much like DirtyCow, we can put a read-only VME here, which is a needs copy and write copy, potentially of a file. And so what this means is that when we then come around while the copy is happening, we encounter this same check again, which says, if the entry is needs copy and it has the writable bit set, then we need to shadow. Otherwise, just continue on and perform the copy. The logic here is wrong in a way that is, once you understand what it's trying to do and what the semantics are meant to be, it's incredibly, incredibly wrong. But if you were to just read through linearly without having the background knowledge to see, well, what's it even trying to do? What are the semantics here? You would not necessarily spot that this is very, very broken. So yeah, it comes through. Rather than performing the shadow operation, creating a copy of that page, you instead end up with a copy from that source VM object to the destination VM object inside the fizz map for a page that you should never, ever be able to write to. And so the question that's perhaps most interesting to this audience is, what can you actually do with such a thing? And it turns out Ars Technica are absolutely spot on with what my motivation is for doing this kind of work, which is to irritate Apple's UI designers with this one weird trick. Because why would you want your iPhone to look like this when it could look like this? Thank you.